All right, this is going to be an introduction to computer addition. This whole last part of the course is, wading out into the weeds at least as far as we can without having any electronics to learn the mechanics of how a computer actually adds numbers together. And so let's first talk about the way we store numbers. Earlier in the course we talked about how to take a number n and to turn it into a binary number. We have bn times 2 to the n, bn minus 1, 2 to the n minus 1, and so forth. b sub 1 times 2 plus b sub 0. But we don't write it like that because it takes up too much space. What we do instead is we'll put it in its binary form as bn minus 1 dot 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 down through b1 and b0, and we'll put a little subscript outside there to say, hey, this number is binary, it's in base 2. And so we could take a number and say let n be 1, 1, 0, 1, 0, 1. I'm just making this up. We could be formal and write it out like that to make sure everybody is base 2. Hey, I've got a number in base 2. But that'll get to be a pain in the backside after a while. So if you're always working in base 2, you can just write it out like that, and then that this is a number in base 2. If you want to recover it, you can say, well, this is to the 0th power, this is to the 1st, this is to the 2nd, this is to the 3rd, this is to the 4th, this is to the 5th. So you could recover it as 1 times 2 to the 5th plus 1 times 2 to the 4th plus 0 times 2 to the 3rd plus 1 times 2 to the 2nd plus 0 times 2 plus 1, which is 32 plus 16 plus, 4 plus 1, and so, oh golly gee willikers, this is 5, this is 21, and so this is 53. Okay, so we represented it binary. Now you may have been told all your life that this is because a computer represents numbers in binary. That's almost true. What it does is it will have a spot in memory. Okay, and I want this is kind of a good mental model to have here. Think of a location in memory as some boxes put together, and one bit, and that's what each of these digits are called, correspond to each of these boxes. And so we could say, take this number that I had up here and put it down here. It would be 1, 0, 1, 0, 1, 1. And put it in the box, each of these corresponding to a memory location. But they don't put the numbers there. These memory locations are little spots in memory where either the voltage is written high, or where we put a 1, written high, or they're written low and we put a 0. And what written high and the high and low refer to is there is some threshold of voltage Okay, where above that we're going to say it's high and therefore translates as 1, and below that is low and translates as 0. Okay, and so all of this is say it's some spot in a computer, and there is a higher voltage here, there's a lower voltage here, and that is how it's dealt with. That is what the computer sees when we see this right here. Okay, it sees the voltage. Okay. Now the computer, like I said, stores it in positions. It breaks up its memory into words. Okay, and so let me start here, and I'll draw out a representation of a word. Okay, so each of these positions is either 0 or 1. Okay, either written high or written low. And so this is a word of length 4. And I think there may have been a day in the history of computers where maybe the standard word was of length 4. It's been kind of all over the place. At a certain point, they got the idea, well, let's do our words in, say, powers of 2. And so you would have a word of length 4. Sometimes you would have, a word of length 8. Okay. And then, you've got a word of length 16. And you see they kept doubling it, right? Because, like I say, they decided to go up by powers of 2. And I think it might be easier to double words than it is just to add single bits on. And so right now, I think we're at a stage in our history where it's very, very common to have words of bit length 64. When I say bit length, it has that many positions where you have a bit that can either be written high or written low. Okay, so a natural question to have is, how big of a number can you store in this? Okay, so let's take a look. Let's start at first with like 4 bits, with n equal to 4 bits. We've got these positions that are either 1 or 0. And say, well, how would you make this number as big as possible? Well, you would put 1 in for all of them, of course. And so you would have, this is 1, this one represents 2, this one represents 4, this one represents 8. So I would have 10 plus 5 equal to 15. Okay, and so if n is equal to 4, the max number is equal to 15. Let's say we weren't going up by powers of 2, because we don't have to. They have made words historically that were of other lengths. Say we have 5 bits, we would have 1, 2, 1, 1, 1, 1, 1, and so this is 1, 2, 4, 8, and 16, and so the maximum here is 15, and I add 16 to 15, and I get 31, and so when length is 5, I get 31. And you might think here a moment, what? This was like 15, and that was 1 less than 16. If I'd added 1 more up here, I would have popped over and got all zeros there. And so, and then when I added it to the 16 there, it's like I almost doubled it. So you can get a formula that, you know, if you got an n here, the maximum number that can get there is 2 to the n minus 1. Okay, so the maximum value that can be represented in n bits is 2 to the n minus 1. Two to the n minus 1 is the max value represented by n bits.